I'm gonna stop sharing, and then you go ahead and share.
Yep.
Cool.
How can I go? All right, the full screen works, right? You can still see it?
Yep.
Okay. I'm Connor. I'm going to be presenting on pwning, or more specifically binary exploitation, because there's some things that some people would consider pwning that aren't binary exploitation, but I'm going to be doing an introduction to binary exploitation today. You hopefully already read my Slack message about this, but this will probably be a longer workshop because I have several exercises where you can try it yourself set up, and obviously I'll have to allocate time for that. And also pwning is just a difficult topic where there's going to be like 30 minutes of prereqs I have to go over before we can actually start. Um, on that, I'm going to talk about the things I expect you already to know, which I'm going to call hard prerequisites. You need to have basic Linux command line experience and like introductory level. Like if you're taking programming one, that's fine, programming experience. Those two things I already expect you to have at least some knowledge of. It will be very difficult to follow what I'm doing if you don't already have this knowledge. Things that would be nice to know, but I'm going to try to teach in a way to assume you have no prior knowledge of, is experience with Python, assembly, or GDB. But like I said, if you don't have any of those, you should be totally fine. I'm going to try to teach in a way where it shouldn't be required, but you will follow along easier if you have any of those. And with that, I'm going to get right into the prerequisite information because I have a ton of stuff to talk about. And we're first going to go over a super basic intro in Python. And the reason for that is because Python is basically the language of choice for pwning, like in 2020. Most exploits you write will be written in Python just because there's good libraries and tools, and it's a pretty easy language to use. And everything that I do today will be in Python. We're going to be using a library called pwntools, and therefore I'm going to go over the basics of Python so you're actually able to use it, assuming you haven't used Python before. Oh, and quickly before I start this, I posted a message both in the Discord and Slack a while ago with the things that you should have if you want to follow along today. So I recommend you follow along. Pwning is kind of one of those things like programming where if you don't have practice, it will be difficult to actually learn if you're just watching me do it rather than doing it yourself. And if you want to do that, you'll need to download a few things. I have the list of things you need in there. So if you haven't already done that before the meeting, I recommend starting doing that now so that you're ready when we get to the part where you can participate yourself. Anyways, right into Python. So Python is relatively simple. So I just demonstrated some simple syntax here. So comments can be started with a hashtag, or you can do the C multi-line style comments with like a /*. Functions in Python are defined like you can see here, where it starts with def, which indicates it's a function, and there's the name and parameters. And there's a few things that are special about Python functions that you may not have seen in other languages. So first of all, Python functions, the indentation matters. So if you've been programming in something like C or Java, your professors probably told you that the C preprocessor literally strips out all the white space. And that's true, it doesn't matter. But in Python, the white space matters. The way Python determines where your function begins and ends is the indentation. Now, you don't have to use any specific indentation. 2 space tabs, 3 space tabs, 4 space tabs, the literal tab character, they all work. But you do need to use something. You have to indent your functions. That is how Python knows that that's where your function begins and ends. And you need to be consistent about it, of course. One other thing that you'll notice is that, unlike in some other languages, there are no semicolons. Now, you actually can have semicolons, but they're not required at all in Python. But so if you feel more comfortable typing them, you can, but they will do nothing. They're completely irrelevant. And one third important thing you'll notice is that there's no types. So if you're used to a language like Java or C, you may have seen how those languages have types on their variables and parameters. In Python, parameters to a function and variables, when you create them, don't have any type associated. Python basically will just use whatever type it is. So if it's an integer, it'll just be an integer type, which means for a function, you can pass any type to the function. We call this dynamic typing. But the important part you need to know is that you don't need to declare any types. So some simple output is, of course, you can print out with the print function. This is equivalent to like cout in C or system ln print line. or system out print line in Java, if you're familiar with those languages. And in Python, both the double quotes and single quotes can be used for strings. They're equivalent, they do the same thing. Unlike in C, where single quotes are only for characters, in Python, you can use either. I prefer single quotes, but like I said, it doesn't really matter. Either will work. You can use the input function to get input. And additionally, for imports, which are equivalent to like imports in Java or includes in C, basically just using code from a library or somebody else's code, you can use import lines, which will import another Python module into your code. And I have two examples of those. The first is importing the built-in time library, which of course is for time-related things. And the second one is the line you will use to import from our pwn tools, which is a library we'll be using to do pwning later. I'm also going to go over a couple things that are in Python that will be helpful specifically for people who are doing pwning. So Python has a concept called byte strings. So strings in Python are, by default, they are not like, they aren't represented specifically by bytes. They're like characters. So in Python, that's not good when you're pwning, because you don't want to like have to deal with like different like encodings and like, it's just disgusting. So you want to be using byte strings if you have to deal with raw bytes. And byte strings, you basically just slap a B on your string and it becomes a byte string. And in Python, a byte string represents a raw sequence of bytes. So Python will never try to convert it like to Unicode or anything stupid like that that'll like screw over your exploit and make it not work when you're using a byte string. And also you can convert between normal strings and byte strings by using the encode and decode functions like I used there. And you specify the encoding like ASCII or Unicode or whatever. And there's a few other things that are useful for pwners. You could also use the ljust function to pad a byte string, which is useful in cases where you get like a partial pointer and need to pad it out. We may have an example of that later. And one other feature of Python that's actually unrelated to byte strings, but is useful for pwners, is converting variables to integers or strings to integers. So the int function in Python can be used to convert strings to integers. We'll actually definitely see an example of that later today. And you can see that you can provide a string and Python will convert it to an integer. And you can also provide a base. So you see I convert a base 10 string and a base 16 or hexadecimal string into an integer. And Python's hex function, like you'll see it works very, very well. It like removes the 0x and everything. And one more thing, we're going to be using the pwn tools library today. So I'm going to go over a few things in the pwn tools library, which hopefully you'll be able to remember for later. So these are in the pwn tools library, not in Python itself, like the stuff I just mentioned. So in pwn tools, you can create this thing called a tubes object by using a few different types of functions. So one of those is the process function, where you just supply an executable on your machine. And one of those is the remote function, which will allow you to connect to a remote machine. So this is really useful in pwn tools because you can use the same type of object for both when you're debugging locally, when you're developing your exploit, and when you're running it against a remote, like in a CTF or in a pen testing environment. Once you have an object like that, you can use a send line and send functions to send data to that program. So send line, of course, just sends what you send and adds a new line to the end, while send doesn't do that. And then you can use the recv related functions to receive data. So for example, I'm using the recv until, which will receive data until it sees that string, and then it'll return what data it received. And then one more important thing is the interactive function, which will instead, so pwn tools, what you'll typically do is you'll program your exploit, and then at the end, you'll switch to interactive mode, which allows you to control directly like from your shell, like put in input and get output. So typically you'll get your exploit, it pops a shell, and then you'll use interactive and you'll be able to access that shell and cat out the flag or do more post-exploitation stuff if it's a pen test or whatever. And one other thing that's in pwn tools that is very useful and you will likely use a lot if you're pwning is packing and unpacking bytes. So now we'll go into this a little bit more later, but essentially in memory, computers aren't storing like 1, 2, 3. Like if you've got 123, the computer isn't going to put 1, 2, and 3 in memory. That's like not efficient. They're stored in binary, which you may have learned in your programming classes. So if you have the raw bytes that make up a number in memory, but what you want is an integer in Python so you can do math on it, you can use the U64 for 64-bit, or you can use U32 for 32-bit, U16, U8, etc. And the pwn tools will unpack it for you into the correct integer, which is really good because it means you don't have to do the work, and it's really annoying to have to do this yourself. And similarly, if you have an integer and you need it in byte form, a common example of this, as you'll see later today when we do an exploit, is if you have a pointer and you need to send it to the program, you'll need to have it in the actual form that it's used in memory. So you can use the P family of functions, again, P64, 64-bit, P32, 32-bit, etc., to convert the actual integer you have into the in-memory representation that the CPU actually would use. Now, I'm going to briefly glance over assembly, but we're not going to try to talk about it much today, but we're going to talk about it a little. So, as some of you may be aware, your computer does not actually run C code or Java code, or at least it very likely doesn't. If anybody here actually has that happening, they have a really weird CPU. So what it actually runs is machine code, and what we do is we compile or interpret other programming languages, which are more easier for humans to write, into machine code. So GCC, for example, will take your C file and compile it into a binary that you can actually run, which is in machine code. Now, the problem is machine code is literally just bits on and off, often represented by zeros and ones. You're never going to be able to read that. Good luck using that. So a thing that we've invented is it's assembly. So assembly is basically just a representation of machine code. So unlike programming languages with C, where you compile it into machine code, assembly is basically a one-to-one mapping. It's just a more human readable form of machine code. So you can use a disassembler to take the machine code and print it out as assembly, and then you'll be able to read like what your CPU is actually doing. And these aren't like things like in C. These are like really low level instructions, like take these two numbers and add them together, write to this memory address, write to the stack, etc. And now this is a really important skill that you will eventually need to learn for pwning. But today we are just going to gloss over it. I'm not going to teach reverse engineering because that could be like a whole topic on itself. For all of today's exercises, I'm going to give you the C source file, and therefore you'll be able to look at the C source file, and you shouldn't need to look at the assembly that much. If you already have some experience and you want to like try like extra hard mode for today's challenges, feel free not to look at the source file. But for today's exercises, you will look at the C source file. But in the future, many pwning challenges seen on CTFs or other challenges will require reverse engineering. So it's a skill that if you're interested in pwning and this looks cool to you, I recommend that you start learning. All right, and now we're going to talk about the stack, because the stack is an implementation detail in your computer that really matters for us pwners and for today's exercises. So the computer, when it's running, has to store stuff somewhere. Now the CPU actually has registers, which are 64 to 32 bits. Essentially all modern CPUs are 64 bits nowadays, but which store information. But your CPU probably only has 10, somewhere between like 10 and 30 registers. That's not going to be able to store enough memory data for all the programs you're running. So we have RAM, of course, which is where you store stuff. And every program on your computer has a stack, and the stack stores certain very important things while your computer is running. So how does a stack work? Well, you may have learned this in a programming class, especially if you took programming 2, you probably have already learned what a stack is. Essentially, a stack is something where you can put things on top and you can take things off the top. So for example, I could put thing 1 on the stack, and then I could put thing 2 on, and then thing 3, and then thing 4, and then I'm going to remove thing 4, and then I'm going to remove thing 3, and then I'm going to put thing 5 on top, and then I'm going to keep removing. So we call an operation where you put something on top of the stack a push, and we call an operation where you take something off the top of the stack a pop. Now, how do computers use the stack? Well, computers use the stack in a way that's very important for us pwners. So when you call a function in your program, how does the computer know where to go back to after you call your function? Because your function could be called from anywhere. So, and your function could even call itself. So how does the computer know where to go back to? Well, the way it actually works is that it puts the return address on the stack, which is just the memory address of the code that it was already executing, and it stores that away on the stack for later. And you can see in my example stack here, for every function that gets called, it creates what we call a new stack frame. And the first thing in that stack frame is the return address. The second thing in that stack frame is the saved RBP, which is always there, but just ignore it because it doesn't matter for today. And I don't want you to get confused, but you will use it later in your pwning adventures. But for now, know that it's safe to overwrite this with all of the pwning challenges we'll be doing today. And one other thing that goes on the stack is local variables for the function. So if your function has variables inside of it that are like local to the function, not like global variables, they will often go on the stack. Sometimes they'll be only in registers, particularly if it's like an integer variable or something. But if it's like a buffer, right, like a big array of characters or something, that's going to be going on the stack. And this is important because, as you'll see later, the fact that the buffers that we're able to read into and the return addresses are on the stack as well is very important for us pwners. However, there's one slight lie that I've told you or like shown you in this image here that anybody who actually knows about the stack may know about. In reality, the stack does not look like this in memory. It looks like this. It's upside down. The stack actually grows downwards. So the stack starts at a high memory address, and when you put something on top of the stack, the memory address actually goes downwards. So this is important to remember, that the stack grows downwards in memory. And as new functions are called, when more stack frames are put onto the stack will grow downwards. Now that we've gotten most of the prerequisite knowledge out of the way, we're going to go over our first easy exploit, which is a buffer overflow. And specifically, it's going to be a return to win style exploit. Now, let's look at this C code. Any C programmers may notice a slight issue, especially if you've written code like this and had your code crash. And that issue is that you see I have an array of characters, but it's only 15 characters, but I'm reading 100 characters into it. Now, if you've ever tried this in your programming 2 class, for example, you'll know that your program is likely going to crash, and that's probably not very good. But crashing a program is boring. As pwners, our job isn't to crash a program, it's to control it. It's to take over the program and force it to do something we want it to do. So how can we do that using an exploit like this? Well, if we know that the name variable that we're reading into, as you can see, which is 15 characters in this getName function, we're reading in 100 characters worth. So we know that we're going to keep writing past the end of that name vector. We have 85 more characters to go. And what happens actually when you write into that name variable is that it's on the stack and it's going to overwrite the thing that's above it on the stack, which in this case happens to be the saved RBP and the return address for getName. Now, and also it may even write into the stuff for main, which will be above it in the stack, of course, because main was the function that called getName. Now, you may notice, well, we're able to overwrite this return address. And you remember what I said earlier, the return address is where the CPU is going to go at the end of the function. So what it's going to look like is it's going to have a return address and it's going to point to somewhere in main. So we have our blocks of code elsewhere in the process, which are just the instructions that you're somewhere else in the process and return to main. What the return if with a different function, something that does something useful for us rather than goes back to main. Well, the processor, it doesn't know that it's not supposed to go there. It just sees a return address, it reads where the return address is, and it goes there. So if we were able to overwrite that return address with somewhere that does something bad that like the original programmer didn't want it to do, well, that would be very good for us and very bad for them. And as our goal as pwners, that's what we want to do. So this is going to be the program that we are exploiting today, or for our first demonstration. I actually have a few demonstrations lined up, but this is going to be the demonstration that I'm going to do. So I'm going to demonstrate this myself. Like I'm going to do it all for you, and I'll show you how I'm going to do it. And then I also will provide a file for you guys to work on after that. So you can see we have a getName function. It reads in your name and then it prints it out, and that's called by main. And we have this leftover debugging code, but you can see in the comment it's 100% secure because it's not actually called anywhere in the program. So it couldn't possibly do anything harmful. So I'm going to get out of this presentation and I'm going to start up a terminal real quick and we are going to start our first pwning challenge. And you can see that all I have is whoops, that's the actual executable. I have the same C file, which is the one that already is there, and then I have it pre-compiled into demo1. So you can see I can provide a name and it'll print out my name and it works exactly how you would expect it to. Now, how can we pwn this? Well, the first thing that I recommend doing when pwning is try to get the program to crash. If you're able to get the program to crash, that means you're on the right track. Because if the program is able to crash, that probably means you're able to control where the instruction pointer goes, where the CPU is executing code from. Now, if you are able to control that to just a random variable where it crashes, that means you might also be able to control it to somewhere which is good for you. So we know that if we write more than 15 characters and we're able to write up to 100, that it's going to overflow onto some useful values in the stack. So I'm just going to run the program real quick, and then I'll just put in, say, a bunch of A's, like way more than 15. And boom, we can see that the program has a segmentation fault, i.e. a crash. Now that's good for us because that means we're on the right track. So now the next thing is how many characters do we have to write to fill up this buffer? Well, now you might be like, oh, it's easy, it's 15. But the problem is the compiler might have rounded that. It may have rounded it to 16 or 32, or it may not have rounded it, or there may be other stuff on the stack that's in a weird order, or there may be other things. So of course, we don't want to just be guessing forever. That would be horrible. So that's where the tool that I had you download called Ghidra comes in. So Ghidra is actually a tool that allows you to disassemble executables. So I'm going to start it up. I've already created a project. The first time you start it up, it'll ask you to create a project. It's really easy. You just make a folder. And then I'm going to import a file, and I'm going to import this executable into Ghidra. And then it should default to all the right settings, and then import it in, and then I'll open it up inside Ghidra's disassembler, and we'll be able to
Connor,
see what the.
could you increase
Sorry.
the font size of the terminal? Some people are having a little trouble seeing it.
Oh no, I don't know how to do that. Oh, I figured it out.
Awesome. Thanks.
Anyways, and once you open up Ghidra, it'll ask you if you want to analyze, and I recommend just for the challenges today, just accept all the default analysis it wants to run and just click analyze, and it'll take a second and it will analyze your function. And then you'll have something that looks like this. And you can see in here, we can actually see the raw assembly that makes up our program. So if I scroll down, we can see different assembly instructions. But reading through all this is going to be horrible, and this is a pretty short binary. So luckily, if we just go over to the functions, we can see what functions, and because I'm nice, I haven't stripped the symbols or anything, so you can see the functions that already exist. So if we go to main, you can see the assembly for the instructions, which, like I said, I'm not really going to go over today, but you will want to know if you really want to get into pwning. And you can also see this decompile. So like I mentioned before, assembly is a one-to-one mapping with machine code. It's basically just a human readable representation of machine code. But one thing that's good about disassembling tools like Ghidra and IDA Pro is they often will provide a decompiler instead. Now, the decompiler isn't perfect because you lose information when you compile a C source file, but the decompiler basically does its best job to guess what the C source code looked like when it was originally compiled. So we can see that it has correctly determined that what main is doing is it's calling the getName function, which makes sense because it's a pretty simple function. And then if we look into getName, you'll see there's actually some variables that didn't actually exist originally in our code. And that's because, of course, the decompile isn't perfect, but we can see it prints out what your name is, and then it reads into a buffer. And what's important is it's reading into this local 17 buffer. And if we look in the decompile in Ghidra, we can see that it'll show you how far away from the stack pointer various variables are. So it's reading into local 17, and you can see that it says stack minus 17 in hex. And the 0x, for anybody who doesn't know, just means hex, which is just a way of encoding stuff that uses 16 characters instead of 10, like base 10, like our normal numbers. So we can see that it's 17 characters away from the pointer of the return pointer on the stack. So that's what this means right here. So that means if we write 17 in hex, so this is actually like what, 23 in decimal. So 17 in hex, 23 in decimal. If we write this many characters, and then we can write whatever we want for the return pointer. So I'm going to quickly demonstrate that by running the program in GDB. So GDB, for those of you that don't know, is essentially a debugger for executables, and it's very useful for pwners. And I also would had people download GEF, which is the GDB like extra something. I don't remember what it stands for, but essentially it's a toolkit for pwners that provides extra information. So there's a few GDB commands that you're going to want to be familiar with. So run will run the program. If you B breakpoint or just B will allow you to set a breakpoint. Disass will allow you to disassemble. So if I do disass main, we can see that it'll dump the code for main. And we can see that it's calling the getName function. And if I disass getName, we can see that it will dump the code for the getName function. And one thing that I'm going to do real quick is I am going to breakpoint on this ret. Now, you don't need to know much assembly, but one that will be very useful for you to know is ret. And what ret does is it is a return. So when you disassemble a function, you'll always see the last instruction will probably be a ret, which is a return. So I'm going to just provide a breakpoint. So all you need to do to provide a breakpoint is just put in the memory address preceded by a star and then B for breakpoint. And we'll see that GDB will tell me that it's set a breakpoint. And then I can type run to run my program. And if I remember right, I said I needed 23 letters to get to the return pointer. So I'm going to put in 23 A's. 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3. And then the return pointer, because this is a 64-bit binary, and 64 bits is actually 8 bytes, we know that the return pointer will be 8 bytes. So 1, 2, 3, 4, 5, 6, 7, 8. Now, if I did this correctly, what we'll see is the return pointer should take from this should be the part that overflows into the return pointer. So when I look at what the return pointer is, I should see that it's all B's and doesn't contain any A's, because this is the part that we use to overflow to get to the return pointer. Now, hopefully I actually know what I'm doing. And we'll see that when it hits my breakpoint, we'll see that because I'm using Jeff and not just like normal GDB, it displayed all of this useful information. So what all the register values are, what's on the stack right now, as well as the what functions are currently executing. And we'll notice that what's on top of the stack right now is all of these B's. So that's actually where it's trying to return to. And we'll actually notice that if I continue, which you can just do by typing C, or you could type out all the way continue, you'll see that we get a seg fault. And why do we get a seg fault? Well, it's because we tried to return, but we tried to return to this address, and this doesn't actually exist. It's just not going to work. So that's good, because that means that we successfully were able to control what the return pointer is going to be. And instead of whatever it was supposed to be, it was RBs. Now what we're going to do is we're going to write an exploit. And by the way, Q or quit just quits out of GDB. We're going to write an exploit for the program in Python. So I'm going to write exploit.py, and I'll just put the shebang, if I can type correctly. And the first thing we're going to want to do in our Python script is import pwntools. And this will get us access to all of the pwntools related things. And then we're going to want to set up a connection to pwntools. So like I said earlier, a tubes object. If you remember, I can use this to start to access a remote process. And then what I'm going to do real quick is just show you how this works. Is essentially this will launch a process. This will launch a like the process, and then interactive will let me control it. So if I run this exploit, you'll see it starts the process, and then it switches interactive mode. And if I put in my name, you'll see it works how we would expect. And then you'll see EOF while reading interactive basically just means that while you were in interactive mode, the program exited, which of course it did. That's what it's supposed to do. Now, instead of just going straight to interactive mode, we're going to try to pwn it. So what we're going to do is we're going to send a line, and we're going to send a 23 or hex 17, hex 17 string of A's. And notice that in Python, you can just multiply strings like this. So instead of having to type out 23 A's, you can just multiply by 23, and that'll just make the string that has 23 A's. And then we're going to add on to that. This time, instead of just something garbage, we're actually going to return to somewhere which is useful to us. So first, what I'm going to do is I'm going to use another Tone Tools feature to import the binary and read in all the symbols. So that's what this ELF does. So when you create an ELF, this is really useful because it allows us to get information about the binary, like where functions are. So one thing that we can do is if I look in the symbols for the binary, I can access various functions. So for example, let's say that I send the main function, then it would return into main and it would just basically loop the program. It would do the same thing. And one thing I'm also going to do that may be useful for you is if you can set the log level in Pwn Tools, and I'm going to do this real quick. And if you set it to debug, it'll show like all of the data that's coming in and out. So what? Oh, I just typoed that this is actually, the executable is of course called demo1, not demo. You can see the live process. And I also, you can see I'm really bad at this. One thing that if you remember before, like I said, is you can't just send a number to the program. You got to use the in-memory representation. So what I forgot to do here is I actually, you'll see that what I did is I tried to add these integer, which is this is what it actually returns. It's just the integer of where it is in memory. And I tried to add it to this byte string right here. But obviously that's not going to work. I need it to actually be in the in-memory bytes format. So if I use P64, I can pack it like I mentioned earlier, which will convert it to the in bytes format. Now, what I can do is if I run the exploit, what we can see is that it will what we can see is that it sent in all of the A's, followed by this right here, which happens to be the in bytes representation of the main return pointer. And we can see what it did is it asked for what my name was, and then I sent that in, and then it asked for what my name was again, and that's because it looped back to main, and then I sent just an empty name, and then the program exited. But this time, instead of sending us back to main, I'm going to send us to that open shell function, and then I'm going to run the exploit. And then we can see that I'm actually in a shell. And this is a complete shell. So if I was running on a remote system, I would have just pwned it. And typically at this point, like I said, if you're in a CTF, there'll typically be a flag file that you can cat out. Or if there is or if you were like doing an actual pen test, you'd want to do post exploitation stuff. Obviously, I'm not going to cover that in the pwning lecture, but you can see that we have successfully pwned this binary. I'm able to send it to the get shell function, and it's able to spawn a shell. And now one thing that I'm not going to do today, but I will quickly demonstrate. So say I was doing this for a CTF or a challenge or whatever, the next step would probably be, instead of running it on my local machine, I would run it on a remote machine. So I don't actually have a remote machine set up today, but what I could do is like if I had a remote machine where I had like the remote and then the port, like say I was doing this for a CTF, I would do this and then I would run it, and you would see Pwn Tools would try to connect. Now, of course, this isn't a real remote because like I said, I don't have anything running, so it'll just error out. But if this was like a CTF, I would be able to connect to a remote machine and pwn it. Now, what we're going to do now is I'm going to give you guys a challenge, and you guys are going to practice pwning. And it's going to be very similar to the one I just did. So if you were paying attention, hopefully you'll be able to pwn it. And of course, feel free to ask for help if you want it. I will drop the files in Discord real quick for you. And then after that, you guys can feel free to try it yourself. So hopefully this works. All right, so that will be the C file, and then that will be the binary. And I'll also upload these to the Slack as well real quick for anyone who is, for whatever reason, only on the Slack. And you can begin downloading these, and you can begin attempting to pwn them. Like I said, this will be your first time. It's pretty simple. Like it's a similar style binary to what we just did. So if you've been paying attention, you should be able to do it. And I am going to go get a drink of water real quick while everyone attempts that. If you have any questions, feel free to ask in the chat or just out loud even. And yes, go ahead. And try yourself, and hopefully you will be able to pwn. And you'll know when you got it right when you're able to run your exploit like I did here. And oh, whoops. You'll know you got it right when you're able to run your exploit, and you're able to access just a shell and able to, and able to run commands and whatever. And if you're able to do that, then congratulations, you got it right. Oh yes, as someone mentions, I wasn't actually here last week when John went over commands, but you will need to chmod plus X to make the binary executable if you aren't able to run it immediately. So like I said, I recommend doing it in a similar step to mine, figure out what you're able to do to get the binary to crash, and then after you're able to get the binary to crash, figure out what you're able to do to pwn it and get control of it. And like I said, I'm gonna go get a drink of water. Good luck.
Hey guys, just a quick announcement. As John told you at the top of the meeting, VCSA was down for some maintenance. Patching maintenance is done for right now, so if you need to use VCSA to run tonight's exercises, you should be able to for the remainder of this meeting. If you have any issues, please message me on Slack. I have to leave the Zoom meeting, but I will try and respond to any messages that you shoot me on Slack. Questions on that environment before I hop off?
Thank you, Ben.
Yeah,
Have a
thanks.
good night, everybody.
You too. Oh, also, if you could just post in the chat or say out loud when you finish, or I guess give up, that would be great, so I know when to continue, because I don't actually know how long this will take for first-time pwners. I see someone just messaged me about trying to compile the C file. You should not do that because it will enable all sorts of protections that are like that won't make you able to pwn it. Use the binary that I provided. Do not attempt to use the C file. I guess I'll post what I use to compile it just in case for some reason the binary doesn't work for you. But if you compile it on your own, it may not work. So I recommend using the binary I provided, but I will post the full if you do need to compile it for some reason, I believe that is what I use to compile it. All right, congratulations. I see that we have one pwn coming in. So if you're still working on it, do your best. It's obviously going to be hard for your first time. So keep going. Oh, also for the people that are still working, if anyone's stuck or can't figure out what to do, feel free to DM me on Slack or Discord what you have so far, and I'll take a look. I'll probably move on in like 10 to 15 more minutes because I have one more demo I want to do, and I slotted for 2 hours, so of course I have to make sure that I have time for that. All right, I'm gonna give like 2 or 3 more minutes, and at 7:55, I'm gonna quickly show the solution to this, and then I'm gonna move into the second and final demonstration of today. All right, it's 7:55. I am going to resume my screen share. I'll quickly demonstrate the solution to this problem for anyone who was unable to solve it or got close or whatever. And then I'm going to go into our second demonstration, which will be the, oh, whoops, I'm opening the wrong thing. Which will be the final demonstration for today. And if you didn't get this one, hopefully you'll have better luck with that one. And if you didn't get this one, hopefully I'll be able to demonstrate it real quickly for you. So if we take a quick look at the file in Ghidra, and then I go to, I think the function was called getName still. Yes. Oh boy, this decompile is disgusting. All right, I will actually look at the C source code real quick. You can see that it asks if you are an admin. Then if you say yes, it will bring you to this new admin debug, which doesn't do anything useful, but it does read in 200 characters to a 50 character buffer. That's not going to be looking very good for the program. I'm just going to quickly find inside this binary where it reads in. Oh, this is, I should not have used such a disgusting binary. I believe the variable it reads into will be local 48. What even is this? Did the analyze not work? Oh my God. All right, we'll demonstrate, because it's difficult to explain this disgusting and I didn't want to go over the assembly, we'll demonstrate an alternative technique to finding out the offset you need. So I am going to GDB the program, and then I'm going to quickly put a breakpoint on the return of getName, like I did before. And then I'll run the program, and then I'm just going to put in a few A's, not enough to overfill the buffer, but just some A's. And we can see I'm going to take a quick look at this, what the stack look. I'm going to take a quick look at the stack, and we can see that if I look around, I should be able to find by A's, which were read in right here. And if we take a look at the return address, which is right here. Oh, I don't think that's all of the A's actually. Let's go another 8 bytes back. And we can see, okay, so yes, this is the actual beginning of the A's. And we can see that from this address, which is where our buffer began, which we read into the A's, all the way to the return address, which is returning into main, which is right here, is hex 48 or decimal 72. So one other way which you can use to tell how much you need to write to overflow is like I just demonstrated. You can just try it out in GDB and then see where your buffer begins, see where the return address is, subtract the two variables, and of course that will work. So now that I've determined that the value I need to write to get to the return address is hex 48 or 72, I'll just write a quick script to do that. As before, I'm going to import pwn tools, and then I'm going to create the process for this, which, whoops, if I could type correctly, is try1. And I'm also going to import the ELF so I can access the symbols, same as what I did with the first demonstration. And then I know that I'm going to need to write hex, what was it, 42, I believe it was, or 70, or hex 48 or 72 characters. So I'll just write that many. And then if I write the return address for I think it was called old admin debug was the one that had the shell in it. And of course, remember, I need to pack the memory address. And then I just go to interactive mode. I believe that this exploit should work. Hopefully I don't look like an idiot. And yes, it did work. So we can see the exploit did go off. And I am able to view all of the files here. So that is good. And now I'm going to move on to our second type of exploit of the day. If you are able to stay for the remaining 30 to 40 minutes to see what that is about, I recommend it. And I will quickly switch to my presentation. How do I full screen this? All right. And we're going to go on to Act 3, or ret to libc attacks. Now, if you looked in the code for the previous function, we had that open shell function, or in the try example, it was old admin debug. But not all the time there's just going to be a function around which automatically calls a shell or does something useful to you. So what happens when you're able to control the return pointer? That isn't the case. So we can see this is literally exactly the same as our previous exploit. However, we've commented out the open shell function. So we can still control the return pointer exactly as we did previously. As a matter of fact, our old exploits looked like I could literally copy paste it and it would probably control the return pointer, but we can't call a function in the binary. So what do? Well, this is when an attack known as return to libc or ret to libc can be of use. So it turns out that there's actually some juicy locations you can be returning to inside the libc library itself. And for those of you that don't know, libc is the C standard library. So it's the library that provides all these functions we're using, like printf, fgetS, system. Like, it's the library that provides all of those functions. So what if, instead of jumping to a function in our binary, we were able to jump to a function in the libc binary? Now that would be pretty good. And it turns out there's, as I'll demonstrate in a moment, there's some juicy locations in libc which will be spawning a shell for us. So now the problem is that libc isn't in a static location in memory. So previously I could just write with the symbols the return address of my the into the return address my function name, because the way I compile these binaries, all of the functions are at the same position in memory all the time. But libc isn't like that. It gets loaded into a random position in memory, so you can't predict where it's going to be in advance. So how do you solve that problem? Well, what you do is you need to get a libc leak, which is a way of finding out a pointer or a memory address of something in libc, which you can use to calculate where libc is. So in this binary, and also in the example that you will be able to do yourself, I've provided the leak for you. I've pretended that you've already gotten the leak through some other exploit or technique, because obviously teaching how to do that would just be difficult. So you can see in here, I actually print out the pointer to the printf function. And the printf function is of course in libc. So I'm actually going to jump straight into the demo for this because there isn't really much more to talk about. Let me get out of my previous demo and get into demo 2. And if we look at here, we have the demo, whoops, and I do this again. If we look at the demo2.c file, it'll look like the same. Just ignore these assembly instructions. These are just to make sure the exploit works on everyone's computer, so just ignore them. But we can see otherwise it looks exactly the same. So I'm going to run demo 2 real quick, and we'll see that it prints out this pointer to printf. And if I run it in GDB and I run the program real quick, and here's a pro tip in GDB, by the way, that I didn't mention earlier. You can actually Control C if you have Jeff installed, and it'll just instantly break like where the program is right now, and it'll act as if you hit a breakpoint. Oh, I need to actually copy the memory address in advance. But if I run the program and then so we have this memory address. So I'm going to copy that real quick, and then let me see what that memory address is. So one thing that you can do in GDB that's useful is if you do info symbol and then a memory address, you can see that it'll say what the memory address is. And we can see that this is the memory address of printf. So if I was to, for example, disassemble main, and I was able to take this memory address, it would tell me that this memory address is the main function, but this memory address is the printf function. And the printf function is at this address, but this will be the same every time I run the binary because of the way I compiled it. This will be different every time I run the binary. So if I run demo 2 again, you'll see that it's slightly different and it's not predictable. So what we need to do is we need to calculate the base of the GEB segment. So if we run the program real quick, what we can do is we can run vmmap, and it'll show the parts of the files that are mapped into memory for this binary. So we can see that there's a few segments in memory dedicated to the program itself. There's the stack, which we of course mentioned before. There's a few things that we don't know about that I haven't taught about, like the vsyscall, and these are things for the Linux kernel actually. And there's the libc binary. And we can see that the libc binary is mapped in at this region of memory. And therefore, what we want to be able to do is we want to be able to determine this start address. Where does libc start? Because if we're able to determine where libc starts, then all we have to do to find out where we want to go is we can just add to where our offset to where libc starts. So if we know a function is 100 bytes after the start of libc, and we know where libc starts, then add those two numbers together, send that into the return pointer, and boom, we've pwned the binary. Now, the thing is there's actually no functions in libc that just spawn a shell for you. So there are functions in libc like system that will call commands, but we have to provide parameters to those. And I haven't really taught you about how you can provide parameters to the function you're calling through returning. So how do we solve this? Well, it turns out that there are actually some locations in libc which may not be the beginning of the function, but if you jump to them, they'll be juicily spawning a shell for you, which is what you want. So there's actually a tool called OneGadget that allows you to extract these locations. So I don't think I actually put this on the list of tools that you need installed, but if you want to do this second demo, you'll need to install it real quick, but it's pretty easy. You can just install it through gems, or if you're on Arch, there's a package for it. There may be a package for it on Kali, I don't know, but it's pretty easy to install. Otherwise, you can just install Roby and then install it this way, and that I'll post I'll post, once we start the demo, I'll post this link in the chat real quick so you guys can install it for yourself if you want to use it. And basically what happens is when you run one gadget, it'll find the offsets in libc. And if you go to these offsets while meeting these constraints, boom, like libc will just spawn a shell for you, which is perfect. It's exactly what we want as a hacker, to be able to spawn a shell. So of course, that means you need to meet these constraints. Now today, I've set the binary up in a way to where hopefully, no matter what libc you have, you should meet at least one of the constraints. So hopefully that will work. Now, if you were running this on a CTF challenge, for example, you would actually have to figure out which libc they had, because of course, when you're pwning on the remote, you can't use the offsets from your libc, you have to use the libc that they have, but that's out of scope for today's demonstration. If we do a second workshop or something, that'll be a future workshop topic maybe, is explaining how you would do something like that. All right, so, oh my God, why you do this to me, Zoom? Go away, whatever. So 1 second, what I'm going to do real quick is I'm going to run one gadget on my system libc, and if you run LDD on a binary, you can just see which libraries are linked into it. And then if I run one gadget on my system libc, you can see that it'll spit out a few offsets in libc that I can use. And you can see that there's various constraints. So the R12 and R13 registers have to be null, or have to be pointing to a null value for you to be able to use this libc, this one gadget. Now, when you run it on your system libc, you may get different constraints. Now, like I said, I've tried to set up the binary in a way where I believe with essentially all libc values, there should be at least one of the offsets that happens to work. But sometimes you may need to do extra work to get it to work. But yes, this, like I said, this one gadget tool is really useful because if you just go to this memory address, you meet the conditions, boom, like you've got a shell. So of course, we're going to do the same thing as before. I'm going to open the binary up in Ghidra real quick. Don't save. And I'll just take a quick look at it in Ghidra, because of course, if this was a real CTF challenge, there's a good chance that I wouldn't even have the C source code, and I would have to look at the binary in Ghidra, and there would be no other way to figure out what the source code was. Fortunately for today, I'll be providing the source code. So you can at least kind of see what's going on. And then if I look at the getName function, you can see that it reads in, and oh my God, this stupid Zoom thing is in the way, and I don't know how to move it. Oh, there we go. And we can see that it reads into this variable, which Ghidra is calling local 17, and we can see that that is hex 17, which, well, it's the same as the first demo. Well, I guess I used the same size buffer, so it's hex 17 away from the return pointer. So I am going to quickly demonstrate this return to libc attack. So this will be a little bit more involved than the previous exploit. I will quickly, of course, set up my Python script as if I could type Python correctly. So of course, import pwn tools as usual, and do the same thing where I am going to create a local copy of the process. And I'm also going to import the process. And one other thing I'm going to do is I'm actually going to import the libc as well I have, which if I remember right, this is the location on my system, and you can run LDD on the binary to see where libc is on your location. So I'm also going to import the libc so that we can do calculations with, oh, whoops, I just backspaced, I shouldn't have. I'm also going to import the libc so we can do calculations with the libc. And now if we remember right, what the binary does is, oh my God, my Ghidra like closed. Here we go. What the binary does is it prints out the printf memory address. So that's the first thing that I will be reading in, is I'm going to read in printf address. And what I'm going to do is I'm going to receive until a new line. Because in this case, it just happens to be that it will, like if you run it, like I said, like I showed, it'll go up to it'll print it out, and then the new line will be the first character that is not part of it. And then I'll just print out the printf address that we found so we can see how this works. that we can see that it works real quick. Oh, whoops, need to, of course. And we can see, boom, it printed out. But we can see there's also a new line on the end of our memory address. And this will often happen when you're using rec v until. Now, one cool thing about Python is you can actually easily strip characters off the end of a string. So if I write, and there's way more powerful stuff you can do with this like string array like syntax as well. But one important thing is you can remove characters off the end of the string by using a negative number like this. So this, for example, will remove the last character, which will be the new line. I could also remove 10 characters, 2 characters, whatever, but I know I need to remove 1 character off the end of the string. And you'll see that this time my printf memory address will not have a new line on the end, which will of course be good for me. And we can see, like we noticed, is that the beginning of the memory address differs slightly. So what we can now do is we're going to want to convert that to an integer because we're going to want to do math on it. So I'm going to convert the printf memory address to an integer by using the int function. If you remember from way earlier in the slides, we can convert a string to an integer like this, and where we supply the string and then the base, and of course it's in base 16, it's in hexadecimal, so it'll convert it, and we'll see that, oh, whoops, did I type something stupid? Yes, I put an extra D. We'll see that it'll be converted to an integer. And of course, a useful thing, by the way, if you want to print out a integer in hex in Python, you can just call hex and it'll convert it to a hex version. And now the next thing we want to do is we actually want to find the base of libc based on the address of printf. So what I'm going to do is I'm actually going to take the printf address, and then I'm going to subtract where printf is in libc, and you can do just by using symbols like I did before, which will allow me to find from the beginning of libc where is the printf where is the printf function if we start at the beginning of libc. And what we do is if we take the printf address and we subtract out the part that is for printf, it'll land us on the base of libc. And one way to easily know that we, oh, and I did something, oh, I need to be printing out libc base, of course, because that's the name of my variable. And one way to know quickly that you got it correct is that it will be 4,000 bytes aligned. So you see how there's a lot of zeros here? That means I did good, because that means that memory addresses in Linux are always aligned to 4,000 bytes. So 4 kilobytes essentially. So that, therefore, we did it good because it's aligned correctly. So we now found the base of libc. Now, if I run my one gadget again, we'll see, I'll just pick one of these and hopefully it works. I know at least one of these should work. And so we'll know that from the base of libc, I can add this offset and it will be my one gadget, which I can use to open a shell. So I will add to libc base and I'll add the value, and then I'm going to print out quickly the one gadget address. And then one other thing I'm going to do is, instead of opening the process like this, I'm actually going to use gdb.debug. And what gdb.debug does is it's like process, where it opens the process, but it actually opens it in GDB for you, which is definitely useful for you. And you shouldn't have to do this, but because of my special setup, I have to do this to get gdb.debug to work. But on most systems, you shouldn't need to do this, so you can just ignore this part. And when I run the exploit, we'll see, oh my god, and I typoed something. What? Oh, I have to put this above, I'm stupid. Okay, we'll see that it'll launch a GDB instance with all, we'll see that it launches a GDB instance, and I'm able to use GDB. And if I continue in GDB, oh, I closed the, one second. I'm just going to put in input in real quick, which takes input in Python, and that'll prevent it from closing out and instantly terminating my binary, which will allow me to actually still use stuff in GDB. So we can see this is the one gadget address that we got. And if we just take a quick look at what is there, we'll see that we landed in this script execute function. And we landed in the middle of this, and we'll see that we landed, and there's some nice exec VEs in here, which hopefully we'll be calling the shell function. So the fact that we landed in the middle of a function that's calling exec VE is a pretty good indicator that we got it right. That our one gadget is where we want it to be. We landed in a valid place of memory in libc, and it's calling exec VE, which will be able to launch a shell for us. So that's definitely very good. So now what we need to do is we need to send that memory address that we've calculated, of course, to overwrite. Now at this point, I've actually forgotten how far I need to overwrite. Was it the same? It was 17. That's right, hex 17 or 23 in decimal. So I'm going to quickly send that amount, hex 17. And of course, I'm also going to send the packed version of our function. And hopefully, if I did everything right, when I do this, we should quickly, oh, and I ran it in GDB. Whoops. And I also forgot to add an interactive, so you can see it just instantly exited instead of giving me control of the shell. So I'm gonna move it out of GDB and put it back to just being a normal process because I am done debugging with GDB. But if you have trouble, by the way, while you're writing your exploit, this is a good technique to be able to run it in GDB and therefore be able to debug what's wrong. And I apparently did something wrong because I got a seg fault. So I guess we're gonna go back to GDB and you can see some live debugging for what stupid mistake I made today. Let's see what has happened. So I have seg faulted. My instruction pointer is pointing to the middle of nowhere. So that probably indicates that I did not correctly overwrite the number of bytes I need to overwrite the instruction pointer, which is weird because I think I did. Oh boy, what did I do this time? I'm going to take a quick look at the stack, I guess. And this is the joy of writing an exploit. Sometimes you make a mistake and you have to figure out what the issue is. Oh, this hasn't actually run yet, of course. Get name. And I'm gonna, I guess you can see some live debugging techniques. I'm gonna breakpoint right before the call to fgetS. And I am going to see what's going on here. And I'll look at the stack real quick. So in fgetS, we're calling to this memory address. Which, if I add hex 17 to it, should hopefully, it does land us on the return address. So I don't actually know why. I don't actually know why I am having issues. Oh, maybe I picked, which was the constraints on that? I think I picked one that should work. So I'm gonna break point on the return and continue until there. And yeah, I should be executing. And it does attempt to load bash. Whoops. Oh my. That is very weird that it does not work because it does attempt to load the process, but it does not appear to actually run the exploit. Oh, it worked this time. I don't know why it worked last time. Maybe I just got bad luck. or I did something stupid where it doesn't work all the time, but it did work this time. The shell has popped. And if anyone is still here and wishes to attempt a challenge like this of your own, notice that it may be slightly finicky, but if you keep trying, you should eventually get it to work. Like I said before, feel free to DM me if you need help or anything like that. But other than that, that is, if this last challenge will be effectively the end of the meeting. Like if there will be no more other demonstrations, I might, if there's still people here, I might demonstrate how to do the try that I'm uploading right now. But other than that, everyone have a good night. Thank you for coming out. If you still have time left, I recommend attempting this challenge as well. And I will quickly upload it both to Slack and what's it called? And Discord. I've already uploaded it to Discord. I am uploading it to Slack as we speak. So I recommend trying this challenge out for yourself, and yeah, that's good to go. If you need any help, feel free to message me on Discord. If you get into pwning, some practice resources that are good we actually have, if you're in the CTF Discord for UFSit, we actually have a guy in there called Guy in a Tuxedo, also known as Matt in a Tuxedo, also known as Ryan, who actually made a nightmare course, which is kind of like a pwn boot camp where he goes through like basically like step by step, like every type of problem. His first couple problems are actually probably similar to the ones I did today, and that's a pretty good resource. I personally learned pwn off the Hack the Box challenges, and I can vouch for those. And also Owen Flanagan, who is like the CTF chair for UFSit, also posted some resources in the Discord recently. And if you ask him for those, I'm sure if you ask him for like pwning practice, he could give you stuff on that too. Thank you for coming out. This has been my pwn workshop. Feel free to work on the try. I will stick around for anybody who does to help them. And hopefully we can see some more pwning workshops in the future for the next steps in pwning for part 2.
Awesome. Thanks, Connor. I recorded this as well, so I'm going to post this on Slack and Discord for people who want to maybe go over it afterwards. People who had to leave early, they can watch it as well. But yeah, definitely, like Connor said, feel free to stick around, try the last challenge, and if you guys have any questions, I'm sure Connor can answer them.